I was too embarrassed to even bring it in.
I was so pissed off about it. I had a good person that actually worked for the first time. I could have gotten like no work done, put it on.
Alright. Did everybody get my email about the car projects?
Yep.
Okay, if you did not get my email, check your email and you should have all the requirements for the car project. Let's go over them really quick.
Is that like half a page of the rules? Or do we get another?
I'm sorry?
Is that like the half a page of rules?
Yeah.
Like a couple lines?
Yeah.
Okay.
I'll show you here in a second. Oh, where'd it go? Slowest car on the road. So here's the criteria for our project, which hopefully you've had time to start on. We're going to have each car released one at a time inside of a 2-meter diameter circle, and a stopwatch will begin timing the car's run. Circle cannot be altered or modified in any way. If the car stops for more than 1 second during the run is ended. When the car completely leaves the circle, in other words, the final part of the car exits the line, the boundary of the circle, then the run will be ended. When the car must be made of the project materials provided. Each car will have 3 trials in the circle. The longest time will be recorded as the time that you have. And between runs, the car may be repaired if it breaks, but it may not be modified or changed in any way. Before any testing, 3 possible designs with drawings, an evaluation matrix, and a final design drawing must be turned into the instructor. So I would recommend that you get that into me by the very latest Friday, so that you can at least have the weekend to work on this, because on Monday we're testing these cars. Here is the grading scale for this. 40% will be participation. So if you complete the design process, the paperwork, and build the car, you have 40% right off the bat, just for getting the stuff done, right? If the paperwork is not quite done, or the car is not quite built by Tuesday, then that will come out of that particular part of the grade. 30% will be the design process, so the quality of your analysis matrices and the process that you follow. So I'll essentially be looking over your paperwork and determining how good a job you did following the design process. And then 30% of this will be performance, based on length of time of the circle, the efficiency of the design by use of materials, and the functionality of the design. How well it works. That particular part of the grade is a curve-based grade, essentially. So essentially the person with the longest time in the circle will get the most points for length of time in the circle. The person with the most efficient design, that used the least materials to the best effect, will have the most points there. There will be 10 points actually for each of these. And then the person who has the most functional design will have the highest points there. Functionality of the design also includes the aesthetics. So, well, aesthetics is kind of split between efficiency and functionality. So that's the project. Any questions? That's going to go. You guys get started yet? Not really, a little bit. Okay. Well, I'm going to mention a few things that I would recommend for you. We're going to just talk about a few things really quick, give you a little head start on research. And the first thing that we're going to talk about is gear ratios. In case you've never had an experience with this, and the experience with gear ratios, let's go to How Stuff Works. That's fun. HowStuffWorks.com. How gears work. Right? So here you have 2 wheels, and you have one bigger wheel and one smaller wheel, and they're connected in the middle so that you always have this contact in the middle. There's no slipping in the middle, and that is done in our case by using gears, the gear teeth, or by using a rubber band in between pulleys. And you have both rubber band pulleys and gears in your pack, so you can use either one you want, or both if you want. But notice that the bigger wheel has a lower RPM. In other words, that round dot moves around fewer times per second than the one on the right. And yet they both have the same speed on the outside edge of the circle. And what this means is that you can use this configuration to change the linear speed of an object even though your rotational speed is changing differently, I guess is a good way to say that. In other words, you can manipulate linear speed with rotational speed, and you can do the opposite as well. You can manipulate rotational speed with linear speed. Right? What's going on here is that the speed of these circles along the edge of the speed of this white circle here and this white circle here, they're actually moving at the same speed along the edge of the circle. But this one has such a smaller circle that it goes around the circle more times. And notice that you can tell they're going the same speed because when they come together, they're moving at the same speed. Right here, they come together and they're moving at the same speed. Even though this one looks like it's moving faster, it's not. It's just rotating faster. It goes around more times per second. Right? So, how do we use this in our car? Any ideas? If we're trying to make a slow car, how might we use this?
Rubber band onto one axle with the smaller wheel there, and have the smaller wheel attached to the main axle, or the drive axle apparently, with a larger gear there, so it'll slow down the speed of the rubber band.
So which one is the wheel connected to?
The large one?
The large one? Okay. So the rubber band is spinning the small wheel very quickly, and the large wheel is going to move very slowly, rotationally speaking, right? Which is what we see here. We see this one on the right, the smaller wheel, moving rotationally. It's winding, going around and around very quickly. And the bigger one is going around much more slowly, right? Okay? How could we use this idea with our wheels? Could we use this idea to design our wheels in any specific way?
You make a really big wheel.
Make a really big wheel?
Put a bigger wheel onto it.
A bigger wheel onto it?
Some of the stuff I saw last night said the smaller wheel goes faster.
Okay, the smaller wheel goes rotationally faster, but does it actually go linearly faster?
The wheel or the gear?
The wheel.
The wheel, from everything that I saw last night on YouTube, the bigger wheels will start off slower and apparently go further, and the smaller wheels go very fast. That
actually has to do with angular momentum. So you're talking about the ability of the wheel to get going is what you're talking about. But you're not actually talking about the end result, which is how fast the car will move as a result of the spinning wheel. So let's think about this in terms of race cars, for example. Very, very fast race cars, do they have bigger wheels in diameter or smaller wheels in diameter?
Bigger.
Bigger. Fast bicycles, bigger wheels, smaller wheels?
Bigger.
Bigger, right? So we have to kind of think about that. Is a bigger wheel going to be better for us or worse for us? Because you think, again, we're thinking, we don't care how fast it gets going. In fact, we don't want it to get going fast. We want it to get going slow. So that's not something we're worried about. We're not worried about accelerating here. We're worried about not accelerating. However, we are worried about the end speed linearly of the car, right? And so we've already decided that maybe if we have a big gear connected to our wheels and a small gear connected to our drive, we can have our drive moving fast and our car moving slow with those gears, right? And if you've ever ridden a mountain bike, for example, you know that if you put your chain onto this small thing in the front and the big thing in the back, you're going to do a lot of pedaling and you're not going to go anywhere. However, neither of those things change the size of the wheel on the mountain bike. So my question is are you going to go faster if you have a bigger wheel on the mountain bike in that same situation or a smaller wheel on the mountain bike in that same situation? For every time you turn the wheel around and it's a big wheel, how far are you going to go? The diameter times 2 pi, or times pi. In other words, the circumference of this wheel is how far you'll go every time the wheel goes around. Right? And how far do we want to go every time the wheel goes around? A long way or a short way?
Short.
So is it going to be better to have a big wheel or a small wheel?
Small.
Right? It turns out to be a little counterintuitive to us. Even though a big gear on the back wheel will make us go slower, a big wheel will actually make us go faster. Okay? So you have to think these things through, and maybe even have to do some experiments. I would highly recommend it. I would recommend that you test this out, because this is part of your research, right? You may find something else new, particularly with the way you set things up, that helps you out, right? So try to remember that just because I've given you specifically sized wheels, for example, in your kit, you're not required to use them as your wheels. You could make different wheels. And you may find that a smaller wheel is not effective the way you've set it up, or it doesn't just work. You may find that it works great. You may find it doesn't work at all. You may find that you can't figure out a way to make a wheel that is nice for this project. But don't just take it for granted that what I've provided for you is the best thing to use, or the way I've provided for you is the best way to use it. So in your kit, you have pulleys, you have wheels, you have gears. Make some designs and get them turned in so that you can start to test those designs. The earlier you start testing them, the earlier you're going to learn whether or not your theories are actually working out, whether or not your designs are actually working out. Because once you start testing, you can redesign all that you want, right? But you have to get those designs into me first before you get going. How do you get 3 different kinds of designs? Well, maybe you'll have one design that uses pulleys, maybe you'll have one that uses gears, maybe you'll have one that uses both. Maybe you'll have one with big wheels, one with small wheels, one with whatever, you know. But try to think outside of the box without going outside of the circle. Okay? So, rubber band power, you can do that lots of different ways as well. I'll give you one little clue on that, and that is that rubber band power only has a finite amount of time that it works. It only works until the rubber band is completely unwound, right? And so there are ways to store energy other than in rubber band power. Does anybody know of ways to store energy in ways other than rubber band power? You can store energy in things like a flywheel, for example. Anybody familiar with what flywheels are? A flywheel is essentially a heavy wheel that you get spinning using some kind of power, like a rubber band. Once that wheel is spinning, then you can use the energy in that spinning wheel to turn other things, right? Flywheels are used in cars all the time. They store energy inside of engines all the time. There's many different flywheels inside of a car. They're not used exactly the way that we're going to use it, and they're not used exactly the way the flywheels are designed to be, are originally designed to be used to store the energy. But it's one possibility, one thing that you might consider. It's not necessarily the simplest thing to do in the world. To design a flywheel-driven car would be ambitious, but if you got it to work, it'd be really cool. And you'd probably be able to get the car to go for quite a while. Of course, you're also limited with your number of materials. You do have some weighty materials, some bolts and nuts and things that you could use for a flywheel type of thing, but it's something to consider. There are more ways to run a car with a rubber band than just connecting the rubber band to the wheels, in other words, right? So consider that. Also, you should consider that rubber bands, the more you stretch them, the more you twist them, the more you wind them up, the weaker they get, right? And this is particularly true when the rubber bands are being wound up a lot, right? When you wind them up over and over and over again, or you wind them up really, really tight, at one particular point. So I would recommend that you make a car design where the rubber band is very easy to change. And that can be considered a repair, right? Because if your rubber band is stretched out, then it has become essentially broken, right? So you can replace your rubber band in the competition if you designed it so that it can be replaced. If you designed it so that it's like, next to impossible to replace the rubber band without taking the whole thing apart, it's not going to happen. So think about that. Think about the ability of replacing the rubber band in between runs if you're using a rubber band. There are other options. Also, a little bit of dish soap on your rubber band helps it to wind up really well. So keep that in mind. Just a little bit of liquid dish soap. Run all of it, just kind of rubbed into the rubber band. Okay, at this point, I'm going to, let's actually go through all these things here, these pages, just to learn some more things that they've got here. There are actually some calculations you can do called gear ratios. And here they talk about some of these gear ratios in this section. So in this we're just talking about the different things that you can do. You can reverse direction of rotation, increase or decrease speed of rotation, move the rotational motion to different axes by turning the gears and using worm drive gears and other things like that. Keeping these things synchronized. And here is the gear ratio. Here they're explaining how the gear ratios work. And then they're going to actually, I think, give us the formula for the gear ratios. Oh, here they're talking about gear trains. So they're using multiple gears together. They're stacked together called gear trains. So that's... Here they show some practical uses of gears. So this is useful. This will be very helpful for you. And your gears are designed to be put together like this. I don't know if you noticed that, but they actually have holes in the gears so that you can put them together in very complex ways. So keep that in mind, that you have that ability to do some of these things. I want to find one where they actually do some gear ratio calculations. Here's a gear ratio chart. Ooh. So here is a gear ratio chart where they're actually talking about the ratio of number of teeth on the gear, right? And the size of tires that they use them in. So here's the gear ratio up across the top, the size of the tire, and here in the middle you're going to get, what are they putting in the middle, the torque? Nope, they're doing the RPM. So this tells you how many rotations per minute you're going to get with these particular gear ratios. And notice that when we have the lower gear ratios, we're getting our lower numbers here, up in this upper left-hand corner. We have lower gear ratios and lower tire sizes, right? Remember how I said that the smaller the tire, the fewer, the shorter distance you're going to go? This shows that right here. So you have smaller wheel, smaller gear ratio, right? The gear ratio being the gear ratio is defined as the drive gear diameter, or drive. It can be diameter of the gear, or the radius of the gear, or the number of teeth on the gear. Either one, any number you want, but you have to use it for both things. So you take the drive gear and you divide it by the driven gear, right? So the drive gear is the one that you're putting power into. The driven gear is the one that the drive gear is putting power into. Take the ratio of that, those two things, and that gives you that number across the top. And then you can see how it works out. The smaller wheels are going to make you go shorter distances. So, anyway, things to study, things to look up. These are the kinds of things you should be researching. And this should tell you exactly, I mean, when you're doing your design, you should know exactly then what gears you want to use and how you want to use them. And you're going to have a little bit of a problem if you go with small wheels, because the gears are going to be bigger than the wheels. You're not going to be able to directly connect them to the axle, because then you'll be rolling along on your gear, because your wheels will be too small, right? So you're going to have a design issue there if you decide to go with a smaller wheel. There's a lot of things to be considered here, so you need to get started right away. I can't think of anything else that I want to cover today. So unless you guys have any questions, I'm going to let you go to work on your design. Any questions? Okay, go ahead and get started. Start researching. Start learning some stuff about gearing. Start learning some stuff about tire size or wheel size. And start designing. Get this done. Also make sure that you're making good paperwork for this, right? You're taking notes, you're making drawings, you're doing analysis of your designs in a very detailed way so that I can see that you are actually following the design process of engineering. Just like we did on our projects before. Just do the same kinds of things, except this time you're drawing it up yourself and you're not following the workbook necessarily, you're just doing it yourself. Okay, so we're done for today. Get working on this project. You've got some time now. You have to take some time at home as well or you will not get this done, I promise.